Right then, good morning everyone. My name is Mark Hambleton. I'm the head of the System and Software Group, the software part of the System and Software Group in ARM. This is a presentation from our architecture and technology team that I'm presenting because the guy that wrote it's not actually here. What I'd like to make very clear right from the outset is what we're presenting here is what we intend to work on, right? So this is an early heads up about what it is we're starting to work on, starting to define. We've got some early prototype work that's going on inside of Embed OS, so Paul can talk to some of this as part of the presentation. But you are not going to see at the end of this presentation, and here, this is where you can get all of the code, right? This is an early heads up so that you guys can give us some feedback, can talk to us, and are aware of what's coming, okay? So along with the working with the upstream rather than dumping a load of stuff on the upstream, this is us helping you understand where we're going. Any questions on the opening statement? Okay, now I wasn't expecting that. Hang on a sec. I'll leave you a talking stick.
Okay, thanks. This is what you expect to go for the software part.
Yep.
But you will present things on the hardware that is already available. Am I right?
So there's one slide in here that talks about TBSA, which is the trusted base system architecture, and how we're extending that to cover the Cortex-M platform. But there's nothing that we talk about at the moment around hardware particularly. There's some discussion about what we're doing with the ARM v8M architecture specification, but nothing specifically to the hardware at the moment. But let's run through it, and I suspect this talk will take about 20 minutes, 20 to 25 minutes, and then we've got time for questions. We've got a number of ARM people here that will be able to answer the questions if I can't. Front row and down here, so if there's something that's missing, we can actually try and dive in after that, if that's okay. Okay? Are we ready? So, secure systems are being deployed everywhere. That's what this slide says. Security in the embedded space isn't a new concept. There are people already deploying secure Cortex-M-based designs, secure Cortex-A-based designs. Each segment has got different requirements for security, right? It's emerging as an interesting topic. I think mobile is the one that's best known because, and I'm taking mine out of my pocket because it's about to ring, because of the identity and the payment system and DRM and all of that sort of stuff. IoT, the device management, so the life cycle management of IoT devices and the identity control are sort of key factors in that space. But then when you look at server and networking in the enterprise space, you've got attestation and secure execution. And then automotive, robotics, autonomous systems, they've got new, evolving, and more colorful requirements for security than we've seen in any of the other spaces. And that's why we're looking at what do we need to do here for the ARM architecture to make sure that platform security is standard, common, and well designed. So TrustZone in Cortex-A, it's been around for quite a while. I hope everybody's already familiar with TrustZone on the Cortex-A. We can do a quick rundown here. So you've basically got, at the lowest level, EL3, which is the highest privilege of any system. That's where ARM Trusted Firmware sits at the moment. So we've got the tech lead for ARM Trusted Firmware if there are any questions on that one later on. But you've then got the normal world, which runs our rich operating systems and our user spaces like Android or some of the enterprise OS distros. But on the secure side, you've then got two privilege levels: Secure EL1, which is where you'd find your secure operating systems, and Secure EL0, where you get your trusted apps. So What we're saying here is that there are already a bunch of standards and a bunch of APIs that exist in that Cortex-A space, and a bunch of standardization that's already that's already happened. So other interesting factors here, I guess, are some of the hardware interfaces that we're already starting to define, like the initial root of trust, and some of the security features like crypto and secure key stores. So this is a model that's been around for many, many years. This is the V8A architecture model. We've already got architecture specifications that cover a lot of the secure services, like the Trusted Board Boot Requirements, TBBR, which defines the secure boot practices to make it compliant with the global platforms specifications. We've also got the TBSA, the Trusted Base System Architecture. I've now got the right words, it's not what I said earlier, which defines some requirements on the SOC subsystem. And then we've got ARM Trusted Firmware, which is ARM's reference or standard firmware solution for the Cortex-A space, which we've recently extended to cover the 32-bit world rather than just the 64-bit world. I think that's all upstream as well now, isn't it, Dan? Yeah. So that's Cortex-A. As I'm sure you all heard in the keynote yesterday when I got to stand on stage and wave my arms around, the recently released ARM V8M architecture specification now brings TrustZone to the microcontroller market. Learning and leaning heavily on what we learned in the Cortex-A space, we've now got the same secure, non-secure partitioning in the Cortex-M world that we have in the Cortex-A space. So, the other thing to note is that we're starting to define the TBSA for M profile. It follows what we did for Cortex-A, but obviously some of the bits that we did for Cortex-A aren't relevant in the M space. It's going to specify hardware requirements for secure M profile-based systems, so MVM, cryptographic keys, trusted boot, trusted timers, TRNG, so the random number generator, and crypto accelerators, et cetera, et cetera. Okay, so more standardization of those low-level hardware features, which should make it simpler to land common software on top of. Okay? But this is I guess, the key to the talk. We're now looking at defining a platform security architecture to help reduce the cost and complexity of developing software for A and M class systems. So we've got a good base in the Cortex-A world. Now it's time to actually extend that to cover the Cortex-A and Cortex-M. So we're also looking to reduce cost and complexity for SOC designers by guiding security use cases, the decomposition of a security use case, and defining some common building blocks in TBSA. So a list of requirements down the right-hand side. Standard high-level functional software interfaces between TrustZone secure and non-secure worlds. So in the Cortex-A world, you'll have seen the SMC calling conventions, which I think is mentioned on the next slide. How do you do that in the Cortex-M world? So Mbed OS has got a way of doing that already. Mbed OS isn't going to be the only operating system running on a Cortex-M. There will be others. We should make sure that we've got the same standard interfaces on that Cortex-M so any operating system can talk to the secure world. Okay? We don't want to reinvent the world. We want to make sure that we are reusing standard industry APIs where they make sense. Okay? So this isn't ARM is going to redefine the whole of the secure world. We're going to reuse what's there if it's fit for purpose and suitable. Define a sandbox security model. There's a slide on that later, so I won't go there. Provide reference implementations that demonstrate good practice. Now, actually, that's one of the really big successes of ARM Trusted Firmware, right? It was a good set of reference code that showed you how to do things the right way, which is now being used in products. So that's a really good outcome for Trusted Firmware because it's become kind of the standard base for ARM v8a designs, okay? So what we're saying here is we'll provide a set of reference implementations, and we're hoping that people use them and they become embedded in the various operating systems rather than everybody having to invent the wheel again. And we need to make sure that we make use of the fundamental hardware platform security functions that we're going to define in TBSA. And so reference code linking into standard hardware components is a good way forward for doing that. So this diagram's probably provided the most amount of entertainment over the last week. The point of contention is this red line. So as I say, this is a work in progress architecture that we're in the early stages of designing. The platform security interface, how far does it go? Does it make sense for you to have a platform security interface that actually just covers the application layer, or does it make sense that it spans the OS kernel and the hypervisor? Well, for PSA to make sense, it needs to provide a common interface for all of the layers of software to talk to the secure side. Otherwise, you end up with fragmentation at all of the various layers. So PSA is going to cover all of those layers just to make sure that we've got that common standard interface. Again, providing access to standard industry APIs where they exist. So we're defining a platform security architecture, but that doesn't mean that we throw away SMCC and PSCI, too many acronyms for a Las Vegas morning. It means that it's going to encapsulate those standard APIs and use them for those platforms. But we will be creating new APIs where they don't exist, okay? Just to make sure that we clean up the areas where people have had to invent their own in the past. Then the other contentious one is the discovery mechanism. It's extremely useful if you've got a common operating system like Linux, so a single binary build running at EL1 in the open side. If it can interrogate secure side to say what functions do you provide, right? Otherwise, you end up with needing to embed platform knowledge into the open side, which isn't such a good thing to do. Does a discovery mechanism make sense in the M-class world, right, where you've got an RTOS that might be, compiled and hard linked with everything that's embedded in that platform? It's one of the areas that we're discussing and debating internally. There are people like me that think it's a really good idea if it's simple enough and lightweight enough. There are other people that think that it's unnecessary and it's overhead. And it's one of the areas that we're going to want feedback from the OS communities and from the platform vendors to tell us what they think, right? It could be that we spend our time designing an API that nobody ever uses and doesn't care about, and people don't care about. That's, yeah? Yeah, good. Sorry, talking to my friend from Zephyr over here, because it's difficult to know in a microcontroller world whether you need that or not, whether there will be that logical separation between the secure and the open side. So that's why we're here today to say, this is what we're thinking about, come and talk to us. You'll notice that we've got a an array of security functions over here. More complex the platform, the more of these little boxes that we'll see, the more important it is to have that discovery API. Because not all vendors will implement all of those secure services, and they certainly may not implement them all in hardware. So it could be that there is a different way of accessing those secure functions depending on the platform that you're running on. Sandboxes, then. So it's going to use a sandbox security model. By that we mean that each security function can be placed in its own hardware-enforced partition. This is a function of V8M. This is a feature that you get with V8M, I believe. I think it's not, the earlier ones don't support, the earlier versions don't support this. I don't understand what the next bullet means, because these slides hit my inbox and I forgot to ask. I don't quite know what reducing the trusted compute base for each function actually means. I'm not sure if there's anybody in the audience that does. Dan, James, Paul? No? But I do know that it basically means that if you've got a security function sandbox, there's no way of those functions actually interfering with the behavior of the other functions in that are implemented secure side. So everything can be mutually entrusted to enable you to source secure functions from different vendors or to implement secure functions differently per platform. So we generically refer to this as a secure partition manager, which with embed is implemented using the embed microvisor. Yeah, that's good. Oh yes, it says it down below. So in embed OS, that is the embed microvisor, but we're actually looking at how we can genericize that functionality so that we can provide that secure partitioning manager secure side, enabling other operating systems other than embed to make use of that functionality. Again, that's something that we're starting to look at the moment rather than it's something that we can deliver now. In the A-profile world, this is absolutely something that could be implemented by a trusted execution environment like Opti, and something that we do now. And then I guess this is the one that's obvious for a A-class core and is less obvious for an M-class core. And so, as I say, please give us some commentary and some feedback on this. We're not intending to replace or redefine any of the existing secure interfaces. What the discovery mechanism is a way of describing to the rich OS world the capabilities of the platform and how to talk to those secure functions. We think that the discovery mechanism will enable a uniform way to discover platform security functions, describing capabilities and ways of accessing them. Right? It'll also provide a framework for you to add new functions that people haven't even thought of. We do expect that the use of the discovery mechanism and the higher level PSA profiles will be segment specific, because it's obvious that some of the things on a mobile phone aren't applicable to a server. Some of the things on a very small connected embedded device aren't necessarily applicable to a mobile phone, right? So it does need to be flexible, extensible, pick the right subsets for you. And again, we're still not completely convinced in ARM that the need for the discovery API exists in the Cortex-M world. We think it definitely needs to be there for the Cortex-A, but we're open to commentary from anybody on that applicability. It's possible. It really depends. In the Cortex-M world, whether you've got a trusted world and an untrusted world that are not built at the same time. It's possible. But then when you look at the capabilities of a Cortex-M now, and some of they're not all Cortex-M zeros where they're tiny energy sipping things. Yeah, you can run an M7 at rather a large frequency range, and you suddenly get to the position where you might have more of a rich OS environment. So I wouldn't write it off until you've actually run to the bottom of it. Yeah. See, I'm defending my assertion in ARM again, yeah? Yeah. Yeah, no, it's good. I do like to see the Linaro CTO and the embed team aligning on their view on that one. It would just be the software guys that are on the other side. This is you. Good.
So, just as a quick intro, because Mark did the start of the presentation, I'll do just one slide. I work at ARM as well. I used to be the lead developer for what was called Polar SSL, which is now called Embed TLS as it's part of ARM. And I'm responsible for the device-side security within Embed within ARM. And as part of that, we are, well, heavily entrenched in the discussions around PSA because it affects both the implementation of Embed as we're doing it, but also about our future thoughts on how we can secure it, because within the Embed world and any other operating system that will run on Cortex-M, we'll need to think about how to separate out the secure parts now that we have capabilities like TrustZone M that give us the ability to do hardware-enforced separation. But even more, we can do similar separation already on a V7M, and we're doing that already with the implementation of the Embed microvisor that provides that box security protection between different systems. So, as an illustration, we'll look at Embed TLS, how that would evolve within Embed OS as part of implementing the PSA there. So, if you look at Embed TLS, it's split into 3 parts. I've mentioned the 2 most important parts here, Embed TLS, which is the TLS library, so really the protocol library, and Embed Crypto, which performs all the software and hardware accelerated crypto operations, all the symmetric, asymmetric, hashing, random number generation, either accelerated, so using hardware capabilities already in the system, or non-accelerated in software form where they're not available. Because especially in the M world, in the Cortex-M world, there's a lot of systems where hardware capabilities for crypto are not available, where they are practically always available in the A world. Well, that's something we need to handle. So, as Mark was showing, we have a secure partition manager. It's very, very small. It says Embed microvisor, so that's our implementation that takes care of separating all the boxes. We have Embed TLS currently on the normal world, so part of the operating system, base capabilities. And what would happen with the PSA, wrong one, that one, with using PSA is we want to reduce the attack surface of Embed TLS because we want to reduce the untrusted code size to make sure that even if a hacker can go into the untrusted world or the normal world, they can't affect all the secure functions such as identity, key encryption keys that are used for the transportation. So what would happen is to reduce the attack surface, we would move the crypto part, which is actually the only part that operates on critical privileged data, into the secure world. Make that into a separate box, if possible. So give that a separate box to reduce the attack surface, and have a very specific generic API in front of that, because that generic API isn't necessarily Embed Crypto related. That would be part of what we're discussing as part of the interfaces going into the secure world, so part of that PSA interface. And that isn't as simple as it looks, because it's not just moving that library over. because normally in every crypto library, or using any crypto library, you as an application are actually constantly storing those keys and moving them back and forth into the crypto functions. It would mean that you would need to move to a system where you're just using references to keys instead of actually having keys and key contexts. And all those references translate into keys on the trusted side. But the advantage of this is that the TLS library, which is big, is the protocol stack which might have issues. MBTLS is very well tested, so security issues there are very, very rare. But in this case, it at least reduces it that it can, at that point, if there's an issue, that it can leak security keys to the system. And not just in that stack, because especially in embedded systems, there's a lot of million driver code in the Bluetooth stacks and in the wireless stacks that are very, very hard to get to the level where they can't be interfered with. So by making this move, we can at least make sure that there's no impact on the rest of the code base. And that is the purpose of the PSA. So, with that.
I had a question for Mike. Are you looking to move...
Sorry, Mike behind you.
On the back, there is.
So just quick question, looking at your diagram there. Is it your intention to move all the crypto or just the public key stuff? Because I'm concerned about record layer performance. Are you going to be doing all the switching backwards and forwards for symmetric stuff as well, or are you just going to put the handshaking over there?
So the intention is to move all the crypto to the secure side. But in most cases, this is only an upgrade instead of a downgrade because the hardware acceleration still takes place on the crypto side. But it does mean that if to be performance effective, you should be looking forward to doing large blob encryption instead of per block encryption on the software side. But it's also an interface kind of issue that you need to solve. But yes, it does impact performance, and you can still do it on the software side, of course. But if you want to do it securely and you don't want that key exposed, you'll have to do it on the secure side. Because otherwise the key will always be exposed in your normal world code. So it depends on the security level that you want to tie into that symmetric code. And in most cases, if it's your protection key for your tunnel to the cloud, you probably want to protect that from the attacker side, because otherwise you can't guarantee the integrity of your data that you're pushing into the cloud. And the integrity of the little data is vital for the integrity of the big data. So, Mark.
And that's why we want to talk to people. This is actually the last slide. As I said, this is just a statement of intent at the moment. So we're going to build on existing security standards. I'm hoping that came through clearly through the talk. Really, to make software developers' lives easier. That's really what we're trying to do here. It intends to prevent future software fragmentation, builds on existing standards, and it will be proven by reference implementations. So the first reference implementation that we'll do is with EmbedOS. I'm expecting, the reason why we're sort of here is we want to talk to Zephyr as well, because we want this to be a collaborative thing with Linaro Lite. Why am I telling you this? Because at the moment we don't have anything to show you about what it looks like other than the pictures that we've got on the screen. It's to give you a heads up. Nobody likes being surprised by changes, by standardization, certainly by standardization that they've not been involved in forming, okay? We do want feedback. This isn't we're going to go away and do this and then we're going to drop it on you, but we told you that we were going to do that. This is we want feedback. And actually, we want to make sure that we align on a common solution rather than having lots of people going and doing their own thing and then having that big fragmented place that we have to go and defragment in the future. So if you do want to have a dialogue about PSA, I really do encourage you to get and talk to Andrew Tolka, who's not actually here at Connect. He's been to many of Connect's. Most people are familiar with him. He's one of our systems architects in our architecture and technology group. If you don't know how to contact Andrew, you probably know how to contact me or contact Dave or somebody in Linaro, but we can get you into contact with Andrew Tolkien. But yeah, please do get involved if you're interested, if you've got opinions on this, and help us understand. I was right, it was the last slide. Any questions, any comments, any feedback? Okay, talking stick to that direction first.
So on slide 8, if you could go back for a bit.
Slide 8.
Yes.
Yeah.
The question I've got is that you were commenting on the type of the APIs, whether that was between app to app or
Sorry,
kernel.
could you hold the mic a bit?
Sure.
Yeah.
Is that better?
Yeah.
So you're talking about the type of APIs. Would you go between the kernels? Would you go between the apps? Would you do both? One model that we've been playing with, of course, is that I think you and I have talked about this, is that some of us might define our secure environment as a different OS kernel within what is typically labeled the non-secure world in your slides. And so using a secure hypervisor, we can kind of do the same thing and excise TrustZone from some of our designs. Not that we don't all love TrustZone. But the question would be, if you're making these common APIs, could you include that within the non-secure world between two OS kernels or two apps in the non-secure world, part of the API definition?
So that's a good one. I don't see why not. It's certainly something that should be discussed with the architecture guys. The PSA is going to be TrustZone focused. So if you're trying to do this using hypervisors and staying in the non-secure world, that's an interesting topic. So you're probably using HVC calls rather than SMCs to get to your secure operating system. Yeah. So that's actually still covered by the SMC calling conventions standard. So I don't see why it couldn't be part of that model. But we'd obviously have to dig into it with you to make sure that we understand what you're doing. But as long as you're sticking with the SMC calling conventions standard, I don't see why not. Because it's just a matter of somebody trapping it at a higher level and passing it on to a different executive. Dan's looking at me, so hopefully that's what I've said is about right. Yeah. He's our trusted firmware lead.
Thanks for that, Mark. Yeah, I think what you said is right. The SMC HVC thing is just a conduit. So if there is an SMC API, then extending it to HVC should be straightforward. I mean, I've not been involved in the creation of all this, but it seems to me some of this stuff doesn't necessarily, how secure does a discovery API itself need to be? You're just knowing what is available on the device. Maybe some bits and pieces it does make sense, but maybe some of it actually, you don't even need to go into the secure world just to find out what's there, possibly.
Whilst you were presenting, I had a number of thoughts that were sort of going off, and so none of these have been structured, right? But one of the things that, being an NXP as I am, we deal with a lot of sort of certification freaks, right? And to David's point, a discovery mechanism in many cases may be essential in order to just validate that the interface on the other side is what you think it is. Not because you're discovering, you're actually confirming or validating. Yeah. And so, and I was starting to freak out until I caught on to the fact that this is really an interface for expressing interfaces rather than an interface. And the use cases where the certification and the attempts to sort of provide some kind of provability or some quasi-provability of security assertions seems to, we have to sort of constrain as much as possible the interface, and that's where all this talk about generic standards, just making it low-hanging fruit for software developers is kind of going to run up against the need to theme things very specifically for the vertical. Yeah. And so where I'm going with this, I guess, is have you been talking to people who deal with certification and security provability to sort of pin down what you should and should not do in defining this interface so that solutions built on top of it will, you know, not be a square peg in a round hole when it comes time to do these certifications?
So that's really the next step for Andrew, which is why we started to publicise this. So come forward and start bringing up these points. So that's a good one. I'll connect you with Andrew anyway. So there's an interesting dialogue to have there. Okay.
Hi, I really appreciated the presentation here and the early access. Reason being, I'm from a small company in Anchorage, Alaska, who has been doing effectively something like was seen in the keynote here yesterday for about the last 5 years. And the biggest issue we have is how can we absolutely guarantee what we're getting from the sensor device is actually what the sensor device is sensing. And I don't care if anybody sees it, but I can't let them jam it. I can't let them change it. I need to know that I'm getting what's there. And I actually have made up kind of a list from the user perspective. This may be the wrong place for this conversation. Feel free to just completely shut me down if that's the case. One of the things we've been looking at is the blockchain, because the blockchain is openly secure. Okay, it's completely open as to how it's implementing the code that makes it go, but you've got your secure data and your discoverable data, and it's a very pretty kind of a system, and it's for a lot more than just micropayments. Okay, micropayments is where people think about it, and so we got to make sure we're supporting blockchain to the deepest level, the trust all the way down.
So I was having a very similar conversation over dinner last night, so that's why Kate's smiling at me.
Cool, thank you. Also, in the industrial world, which is where we're deploying systems, they are living in a different world. Their PLCs look like our Arduinos now, okay? Maybe, sort of. The Arduinos are actually more powerful. And what's happening in computing is you're determining the new generation of what they're going to end up using, but there's going to be a really hard transition for them from what they've been used to now, because there's concerns in this world that we don't have that they do. For instance, they want something to last for 30 to 60 years, okay? You put it in, it better keep running, and if it's got a problem, it A, better fix itself, or B, better scream for help, okay?
Yeah. That's actually the world I started off in before I started doing this, so I understand that one.
The next thing, and if it needs a reboot, it needs to figure that out and do it by itself. And it needs to warn that that's what happened, that's why you get some weird data,
and then it
et
needs to
cetera.
work out that every bit came back up again, and it's the bit that it was expecting to see.
Uh-huh,
Right.
and I didn't send false information because of an initialization state.
Yeah.
Then the next thing is, it's unacceptable to do wireless only. Wireless is cool, wireless is sexy, but wired has advantage in that it can't be jammed, okay? And you can supply power. You don't have to deal with maintenance of batteries or what happens to the system when the battery gets low, okay? So every device that's built should include an Ethernet port if at all possible, or something reasonably equivalent. There should be nothing that's wireless only. Wireless, wonderful option. Lots of flavors of wireless. Great world we're moving into, but don't delete the wired. And then, yeah, I think that was pretty much what I was hoping you would address in some way. And that's at a higher level than this, but I also understand that the devil is in the details. And if you get the details wrong, which is why you're here, thank you, then when it gets to the level that I'm trying to use it, I can't.
Okay. Yeah, okay. Good. Anybody else?
So on a related note, already before we break up. No, I'm not questioning. I'm putting a statement. On a related note, for people interested in the Cortex-M security partitioning and what we're going to do and what we can do and can't do, tomorrow at 12:10, I'll be hosting a security mini conference on Cortex-M, so in ballroom B, if I'm not mistaken. So if you're interested in that discussion, please join.
Okay, good. Well, thanks. If we've got nothing else, we'll finish. Oh, nearly got there.
Very useful and informative presentation, but it's really difficult to have a effective security discussion without discussing the attack vectors and the various ways to compromise different parts of the system. You didn't really touch on that.
On that? Yeah.
So, yes, you're correct. You can't really put out a good security profile without having a threat matrix and a threat environment that you're trying to protect against. I guess with the PSA, we're extending what we're already having and seeing as a necessary part for, well, most, if not all, IoT and embedded devices to have in order to survive in the world that we're going to go to with billions and billions of devices there. It doesn't mean that each and every system needs to have everything in hardware or not, because that's a cost, a decision based on cost of what the chip is gonna cost. And again, that's a use case scenario where you need to decide that threat scenario. But what we're trying to do with PSA is at least provide a generic interface for all the different parts that you might need to be able to make more secure in either a secure world or a hardware accelerated world. And at least have that available for each and every use case that we can now do in a generic sense. And there will always be cases where this won't be enough. I mean, especially at government grade and higher, this is not enough because the different attack profiles that state attackers could use are way different than what we're protecting against in a generic world of IoT and embedded spaces. But yes.
A specific concern is that with IoT, the devices are subject to both network attack as well as physical attack.
Yeah, they could be, yeah. But the level of physical attack that they can be subjected to depends a lot on the actor that can do that. And the importance of that depends a lot on what the importance of the data in the individual device is. And in most cases, that individual device doesn't contain very important data. It's just a combination of all that data that becomes important.
Actually, I have to respectfully disagree, because in addition to the function of the device, it's pretty much by definition also an entry point into your network.
Sure, that's the case, and that will always be the case, and you can never, well, you can't prevent that. But it's a question of cost. Nobody wants to pay
exactly.
$200 for an IoT device.
It's a question of cost, which purchase price is one element of the cost.
Yes.
To be fair, what they were presenting here is an interface and a set of building blocks. This isn't a discussion on security. Those are mechanisms that underpin building good security. But it's a good point, and the conversation I'd like to hear. Is there a more general, is that what the conversation tomorrow is about? Is there more general kind of around security, the attack vectors, and thinking like this gentleman's just exposed?
Tomorrow is an open discussion on things like attack vectors we see and what we need to do there, and a number of aspects in that world.
Okay. Did you want more?
Maybe I'm just piling on needlessly, but am I correct in understanding that this is really just a logical layer that all the underlying hardware guarantees or lack thereof are kind of orthogonal, and that this is an attempt to not reduce the underlying hardware security by providing a robust as possible logical layer on top of it.
Yeah, so the PSA is the logical layer on top.
Right.
TBSA is intended to specify the minimum logical set of hardware features that you need for a secure system. So TBSA is to try and make sure we've got the right components in hardware. PSA is the logical interface to enable you to use them. Okay.
Any chance of them being proposed as some kind of common criteria profile?
Say it again in a different way.
Understand the words, not the sentence.
Yes.
Yeah, I didn't mean to give you word salad, but you're referring to some kind of baseline set of assumptions about a hardware architecture that would meet some level, and I hate this word, but let's stick with it, right? Security level.
Yeah.
Would you consider proposing that as a template for a kind of common criteria profile that allows a device to essentially be certified against it?
That's an interesting proposal.
Otherwise, it seems that it's just it's a list of aspirational statements, thou shalt or thou should do these things. But
that's definitely interesting. That's worth us talking with Andrew. I don't know what his plans are in that area at the moment because it's at the beginnings. But if that's useful, then that could certainly be considered. Yeah. Okay. Good. Anything else? Okay. Thanks very much, everyone.